So good morning. So first of all, I would like to acknowledge Professor Polivka for having invited me to this summer school and workshop, and it's a pleasure for me to make a presentation about nonlinear effects in thermoacoustic engines. So the title of my talk is Nonlinear Effects Saturating Wave Amplitude Growth in Thermoacoustic Prime Movers, and I just want to change the end of this title because it's impossible for me to make a complete review of the topic. So this will be just an overview, and I hope that the contents will be convenient for you. So this is a plan of my talk, which will be decomposed into 3 parts. The first one is a brief introduction to basic concepts of thermoacoustics and a presentation of the linear thermoacoustic theory, which is used for the design of thermoacoustic engines. The second part of my talk will be devoted to a small review of some nonlinear processes that saturate wave amplitude growth in thermoacoustic engines. And the third part will be also devoted to nonlinear effects, but I will make a focus on the dynamics and more precisely on the transient regime of thermoacoustic oscillators in order to point out that finally we do not understand very clearly what occurs in this simple device. Okay, so let's begin with the first part of my talk. So, as all of you know, there exist 3 elementary sources of sound emission in acoustics, which are associated to 3 conservation equations, which are the continuity equation, the momentum equation, and the energy equation. So when making thermoacoustics, we are interested in this last equation, so sound emission by unsteady heat release. And it's worth mentioning that such a problem is generally more complicated than a sound emission, for instance, by a pulsating sphere, because mainly for 2 reasons. The first reason is that because we are interested in unsteady heat transfer, we should account for the thermal conductivity of the fluid. And the second reason is that this unsteady heat transfer source term depends in a complicated way on acoustic variables, and this may lead to self-sustained oscillations. Okay, so here are 2 famous examples of autonomous oscillators driven by heat, which are the so-called thermoacoustic laser, which will be the core of this presentation, and also the Reischke tube. These 2 devices look very similar, but actually they are different in many aspects. In the case of the Reischke tube, the self-sustained oscillations are driven by a hot grid combined with a mean flow, while in the case of this thermoacoustic engine, the self-sustained oscillations are driven by a temperature gradient in a porous medium that we call a stack. So this device is prototypical of the problems that we encounter when designing thermoacoustic engines. And it is very simple in terms of geometry, but above thresholds, it has some complicated operation, and this is what I will discuss today. So let's go to a picture of this so-called thermoacoustic laser. So this device basically consists of a duct, which is open at this end and closed by a rigid plug here. And inside this device, we place what we call a stack, which is an open cell porous material. And at this side of the stack, we coil an electrical heat resistance in order to impose a strong temperature gradient in that direction. And above a critical value of this temperature gradient, we will have the onset of self-sustained acoustic oscillation at the frequency of the most unstable acoustic mode, which is generally the first mode of this waveguide. Okay, so the next question is, how does it work? So when introducing students to this kind of device, it is quite usual to adopt a Lagrangian approach and to follow a gas parcel which is submitted to a standing wave in a channel of the stack which is submitted to an axial temperature gradient. And in this simplified approach, we decompose the motion of the gas parcel and the heat exchanges within 4 stages, and it is possible to show finally that if the temperature gradient along the wall is larger than the temperature gradient which is experienced by the gas parcel due to the acoustic motion, then we can produce acoustic work with a thermodynamic cycle which looks like the Brighton cycle. But actually the processes are much more complicated because heat exchange occurs continuously, and also a key point is that we need an imperfect thermal contact between the oscillating fluid and the walls. And the gas parcel should be at some distance delta kappa, which is the acoustic thermal boundary layer thickness, from the wall, because if it's too close, the process is isothermal. If it's too far, the process is adiabatic. And then we have the threshold of the thermoacoustic instability as soon as sound amplification is larger than viscous and thermal losses in the device. Okay, so in terms of equation, it's not so difficult to describe this device. We simply have to describe the propagation of plane waves along a duct which is submitted to a temperature gradient. And afterwards, it is straightforward to describe the work production per unit volume and also the heat transport by sound, which are both expressed as the product of first-order quantities. So to that purpose, we assume we have, for instance, a cylindrical duct, which is submitted to a temperature gradient, and we will make the traditional assumption of the linear approximation of acoustics. We will also consider that the typical wavelength is much larger than the duct radius, so that we will assume that we have plane waves. And we will also make the boundary layer approximation for which the transverse gradients are much larger than axial gradients. We will also assume that there is no mean flow, that the gas is an ideal gas, and that both the thermal inertia and the thermal conductivity of the walls is much larger than that of the fluid. So, from the above-mentioned assumption and from the governing equations, we can express the cross-sectional average acoustic velocity, the temperature oscillations and the density oscillations in terms of the pressure and the axial pressure gradient. And therefore, we can obtain a wave equation, which is this thermoacoustic wave equation. So, in this equation, there are some viscous and thermal functions which describe the thermoacoustic process. And these functions depend on the ratio between the thermal and the viscous boundary layer thicknesses to the radius of the duct, and they also depend on the geometry of the waveguide. So this equation is not easy to solve analytically, but we can solve it easily using, for instance, finite difference method. But we should mention also that in this equation, the temperature gradient also depends on the pressure because it is transported by sound. So we need to couple this equation with an equation that describes heat transfer. So now let's go to the description of sound amplification. So the definition of this sound amplification is that it is so the power produced per unit volume by the thermoacoustic effect is defined as the axial gradient of sound intensity. And it's possible to decompose this term into 4 terms. In these 4 terms, we have first losses. So these are thermal losses, these are viscous losses. And the 2 other terms describe the amplification of the wave due to the thermoacoustic effect. And this term corresponds to, so it is proportional to the temperature gradient and to the imaginary part of the acoustic intensity. So it represents the standing wave component of the work produced by the thermoacoustic effect. And this component represents the traveling wave component of the sound produced by the thermoacoustic effect. So in the same way, we can describe the heat transport by sound due to the acoustic motion, which is defined as follows. So it's the time average of the product between acoustic entropy and acoustic velocity. And also we can decompose this term into three terms: a standing wave component, a traveling wave component, and another component which depends on the temperature gradient. So let's go back now to the amplification of a standing wave. And let's consider once again this device, which is the thermoacoustic laser. So in this device, we mostly have a standing wave. So acoustic work should be produced mostly by this component of the work production. And so this component is proportional to the imaginary part of this function in which we retrieve the functions f kappa and f nu. So we can calculate this work production for different geometries of stack. So for instance, a cylinder, a square channel, or even a more complicated geometry that we call a penelet stack. And what we can see here is that, first of all, the work production is more efficient if the hydraulic radius of the channel is slightly larger than the thermal boundary layer thickness. So this means that we need an imperfect thermal contact. And we can also see that this function, which should be bounded between 0 and 1, this function is always significantly lower than 1. So this means that this process is intrinsically irreversible. And this is due to this imperfect thermal contact. Now, if we consider this term of work production, we see that it is proportional to the real part of this function. And we see that the real part of this function can approach unity if we have a traveling wave phasing between pressure and velocity, and also if the thermal boundary layer thickness is larger than the hydraulic radius. So we should have better performance by using a traveling wave engine. So the next question is how to build a traveling wave engine. So we need to first have a traveling wave phasing between pressure and velocity, so they should be in phase. And we need to find a waveguide arrangement around what we call now a regenerator in such a way that we will have a cycle which is close to a Stirling cycle. So this idea was first put forward by Sepperley, who tried to put a regenerator inside a closed-loop waveguide. And however, it did not succeed in generating the self-sustained oscillations. And 20 years later, Yazaki succeeded to onset self-sustained oscillations in a closed-loop device, but he used a stack so that this engine is also irreversible. But 1 year later, Backhaus and Greg Swift have succeeded to build an engine which is a traveling wave Stirling thermoacoustic engine in which we retrieve this closed loop, but we have an acoustic load which is connected to this closed loop. And due to this, we will have inside the regenerator, and only inside the regenerator, we will have a traveling wave phasing, and also the velocity of the acoustic velocity will be sufficiently small so that the thermoacoustic amplification is larger than viscous losses. And so it works, and it works quite well, as I will show in the next slide. So here are two examples of thermoacoustic engines which have been both designed at Los Alamos by the team of Greg Swift. So this is a standing wave engine, so we recognize this straight duct. So we have a standing wave, this is the stack, and this is the acoustic load. And this device can provide up to 600 watts of acoustic power to the load with an overall efficiency which is almost 10%. Now this device is the traveling wave heat engine, so we recognize the loop here. Inside this loop we have the regenerator, and this is the acoustic load. So this device can provide up to 700 watts with an overall efficiency of about 30%. So the efficiency is high, and it is much higher than in the standing wave engine. Please note that both devices use a fluid which is pressurized helium. So this is only to increase the power density of the acoustic waves. Okay, so the topic of this talk is not devoted to the application of thermoacoustic engine, but I should discuss it a few. So these engines have the advantages that they are simple, so potentially robust. They use working gas that are environmental friendly, and they can achieve good efficiency. They also have some limitations, notably in terms of output power, which is limited to a few kilowatts, and their efficiency should be improved. And also, the development of these engines is by now only limited to a few research laboratories. In terms of applications, one of the promising applications of these engines is waste heat recovery. So we can imagine, for instance, this kind of device. So from the waste heat, we can generate an acoustic wave within this device, and this acoustic power can be transformed into electric power using a linear electrodynamic alternator. And such a device can achieve some efficiency up to 18%, which is not so bad. Okay, now a few words about the basic modeling of these engines. So what we do to design such a thermoacoustic engine is that first we use a two-port modeling of acoustic propagation through a device like this, for instance. And from this two-port modeling, under an assigned temperature distribution along the device, we can get a characteristic equation from which we will obtain the frequency of operation as well as the thermoacoustic amplification rate. And also we need to couple this two-port modeling with an energy balance that accounts for the heat transport by sound. So let's assume we have this device. What we do is first that we put a heat input, and we first assume that we have no acoustic waves. From this heat input, we can calculate the temperature distribution along the device. And from this temperature distribution, we can calculate the spatial distribution of the acoustic field, from which we can calculate the thermoacoustic amplification rate. And therefore, we can calculate the heat transport by sound. And we repeat these steps until we have the thermal equilibrium. So this is the basic idea of the design simulation tools. Just a few words about the two-port modeling, but I will be very short. So if we want to describe acoustic propagation through a very short piece of a stack which is submitted to a temperature gradient, what we can do is make use of an electroacoustic analogy and demonstrate that this is equivalent to an electrical two-port with an acoustic mass, an acoustic compliance, a viscous resistance, a thermal resistance, and this term, which represents a source of volume velocity, which itself depends on the input velocity, with a gain which depends on the temperature gradient. So, by this means, what we can do, for instance, in the frame of a lumped element assumption, is to describe some engines which are not, strictly speaking, thermoacoustic engines. So in this example, we have a three-piston Stirling engine, which is called the fluidine engine, and which uses liquid pistons. And so we can describe this using a simple electrical modeling of the acoustic wave propagation. Now, if we cannot make the lumped elements assumption, we simply use the transfer matrix formalism, which describes the pressure and the volume velocity at the output of a piece of the duct from the pressure and the volume velocity at the input. Okay, so we obtain such an electroacoustic analogy from which we get the working frequency and the thermoacoustic amplification rate. Okay, so this is for the linear theory. And the problem with this linear theory is that it is limited to a linear description, so a low amplitude description of these engines. It is also a one-dimensional description of the phenomena, but it's not sure that the temperature distribution is only one-dimensional, and it only predicts the performance of the engine in a steady-state regime. So we need to discuss the nonlinear processes which are responsible for the saturation of the thermoacoustic instability. Right, so first of all, let me remind that a thermoacoustic engine is an autonomous oscillator which is driven by heat. So by nature, the processes that control the saturation of the wave to a finite amplitude are nonlinear processes. So in this picture, I have tried to represent the different processes which are responsible for the sound saturation. And what I will do now is discuss each of these effects one by one from the academic standpoint and also from the engineering standpoint. So let's begin with the first processes that I have already discussed because it is in the linear theory of thermoacoustics. So this is the thermoacoustic heat flux. Okay. So normally I should not need to discuss this effect because finally we know that in any heat engine the work production is always accompanied with heat transport from a hot heat exchanger to a cold heat exchanger. And the definition of this heat flux is clear. It is reminded in this expression. But things are not so simple. The problem is that we have to describe wave propagation through the stack, and this information is within the functions f nu and the function f kappa. The problem is that we can only describe analytically these functions in case of simple geometries, like circular ducts or any other. But in actual engines, in actual high-power engines, what we use is some more complicated geometries, like some pile of stainless steel mesh grids, or some metallic foams like nichrome foams or carbon foams. So these stacks or regenerators have a complicated geometry. They are anisotropic, they are tortuous, and so we need to describe these thermal and viscous functions for this material. So what we can do is to measure them. So for instance, this was done by Whelan and co-workers who have measured, so they have developed an experimental setup, which is presented here, which consists in measuring the complex compressibility of the sample material, which is placed here. So what they measure is they make a simultaneous measurement of an oscillating volume and of an oscillating pressure. And from this complex compressibility, they can calculate this function f kappa. So in this picture, you can see the evolution of the real part of this function and the imaginary part for the case of a carbon foam. And we can see that we can make a fitting with a parallel plate stack for which we fit the distance between the walls. There exist also other approaches which are used in the software Delta EC, which is a very famous software for the design of thermoacoustic engines. So it is based on the calculation of viscous drag and heat exchange coefficients from some correlations that we can find in some reference textbook like the Case in London. And we simply have to adapt some well-established results in steady flow in the case of oscillating flow. So it's a pragmatic approach, but its validity is questionable because we need to make an assumption of quasi-steady flow. But actually there's another problem, which is related to the description of heat transfer through a stack. Because the only knowledge of this function is not sufficient. In a real engine, What we know is the heat what we provide to the stack. And to calculate the thermoacoustic amplification, we need to know the temperature distribution along this thermoacoustic core. But if we do not know the thermophysical properties of the stack itself, which is highly anisotropic, then we cannot do anything. So, even we can wonder if the one-dimensional assumption for the temperature gradient, so is the temperature gradient uniform along the cross-section of the waveguide, this assumption is, I think, not valid within the stack, so the plane wave approximation itself is not valid. So what we can do, for instance, and a solution that we have explored in our lab, is to get this information of heat transfer phenomena from the measurement of an acoustic transfer matrix. So we use a black box approach, and by measuring the transfer matrix of this thermoacoustic core under different values of the heat input, then we can calculate the thermoacoustic amplification rate without knowing the details of the temperature distribution or the details of the structure of the material which is used as a stack. So I won't go into the details of these papers because this work because it would be too long, but if you can read them, the references are there. I'm sorry, it's maybe too small for you to see. Okay. Okay, so now I will continue with a second saturation process, which is the effect of nonlinear acoustic propagation. Okay, so if we want to evidence this effect, a simple way is to start with the one-dimensional equation of acoustics without dissipation, but without linearization as well. And so this is this equation. So here we have the momentum equation, the continuity equation, and an expression, an equation that tells that we have an adiabatic process. We can try to find a particular solution to this set of equations in the form of a simple waves that travels along the increasing x, and we can show that this simple wave equation is the following. The interesting feature of this equation is that it tells that a compression wavefront will move faster than a depression wavefront. So after some distance of propagation, the wave will be distorted. And in terms of frequency, this means finally that we have a cascade process of higher harmonic generation. And this should impact the efficiency of a thermoacoustic engine because the losses are proportional to the square root of the frequency. So if we have a spectral enrichment, we also have an increase of the losses. And another reason is that a thermoacoustic engine is always designed for a particular frequency, which is that of the fundamental mode. So if we have higher modes, they do not participate to the thermoacoustic wave amplification. Moreover, this effect of higher harmonic generation can be promoted by the resonator itself if the resonance frequency coincides with that of higher harmonics. Okay, so the problem of nonlinear propagation of acoustic waves has been very extensively studied in many fields of acoustics, and it has also been studied in the frame of thermoacoustic engines. So for instance, in this picture, you see a numerical modeling which presents the transient regime of wave amplitude growth in a standing wave engine with a stack which is submitted to a constant temperature gradient. And we can see here a strong asymmetry in the wave, which reveals that we have a lot of harmonics in the signal. And these harmonics are, in the computation, they are responsible for the sound saturation. There has been also some other works, for instance by Ilinsky, that were devoted to calculating the optimum shape of the resonator that will maximize the nonlinear quality factor of the resonator. But I have to say that such kind of study has never been compared to experiments, and to my knowledge, there is no experimental evidence that we have such a strong asymmetry due to higher harmonics generation. And it seems that higher harmonics can be present in a thermoacoustic engine, but it's not sure that they are responsible for a great amount of dissipation. So, generally, we do not account for this effect for a first modeling of a thermoacoustic engine. However, even if it is not a predominant loss mechanism, it is still interesting to look at the process of higher harmonics generation. And it is worth mentioning that recently, Dr. Biwa from Japan was the first to observe the generation of shock wave due to the cascade process of higher harmonic generation in a closed loop stack-based thermoacoustic engine. So, what we see in this picture, I hope that you can see something. We have the pressure signal as a function of time at different locations along the loop. And we can see on these signals that we have shock waves here that travels clockwise in the loop. The interesting thing is that if we take this stack with the same temperature gradient, but if we place this stack in a standing wave arrangement working at the same frequency, we won't observe a shock wave. And so Dr. Biwa has shown by the measurement of acoustic intensity that in the case of a closed loop, not only the fundamental but also the first harmonics are amplified through the stack. While in the case of a standing wave engine, the higher harmonics are damped through the stack. So this may be the reason why we can observe a shock wave in this configuration, but not in that configuration. So it will be interesting to try to reproduce these experimental results using an adequate modeling of the phenomena. Okay. So now we'll discuss another mechanism which is called acoustic streaming. So acoustic streaming refers to the generation of a steady flow due to some viscous effects in the boundary layer. So this steady flow is generated by the acoustic motion. So this is called acoustic streaming. Okay, so to make an evidence of this effect in a simple way, so let's start with the Navier-Stokes equation. And let's make the boundary layer approximation, and let's use a successive approximation method with an expansion up to second order. And so if we do so, and if we make the time average of the x component of the Navier-Stokes equation, we show that finally the second order time average velocity is not zero, and there exist some source terms which are here that drive this streaming, this acoustic wind. And in this simple derivation, these source terms are first a quadratic term in the convective derivative, and second, a term which is due to the fact that the viscosity of the fluid will depend on the temperature. And due to this, during an acoustic cycle, the gas parcel will experience a net drift, which is simply due to the fact that it will not experience the same viscosity in this way than in this way. But actually, there are many other sources of acoustic streaming in some most real cases. What we know also is that in the case of a standing wave resonator, the spatial distribution of acoustic streaming is as represented here. So we have some, let's call outer streaming cells, so far from the wall, which turn like this. And we also have some inner streaming cells, which are close to the wall. And what we know also is that the spatial period of these cells is a quarter of the wavelengths. Now, in the frame of thermoacoustics. So since the pioneering works of Lord Rayleigh about this topic, there has been a renewal of interest in studying acoustic streaming, and notably in order to get a deeper physical insight on how it impacts the operation of thermoacoustic engines. So, here is a list of some relevant papers in the field, so I won't go into details. I just want to emphasize some important points. So first of all, what we know from the works by Mingui and Gilbert is that as soon as the acoustic level is so high that this non-dimensional number, which is the non-linear Reynolds number, which is defined as the ratio between the acoustic Mach number and the shear number. So if this number approaches unity, which is the case in thermoacoustic engine, then we should account for inertia effects in the description of acoustic streaming. What we know also is that the description of acoustic streaming is different in the case of a closed-loop traveling wave engine than in the case of a straight duct. Because in this kind of thermoacoustic engine, the existence of a closed-loop path makes possible that we have a unidirectional streaming mass flow that goes in this direction. And this will convect a lot of heat. While in the case of a standing wave engine, we know that we cannot have a cross-sectional average of this second-order streaming mass flow. This cross-sectional average should be 0. So it's an important difference between both. So this kind of streaming is called Gedeon streaming, while for this streaming we refer to Rayleigh streaming. Okay, so now I would like to present a few experimental results in order to show that finally acoustic streaming is not very well understood in thermoacoustic engines. And let's begin with the works by Thompson and Hatchley from Penn State. These are experimental works, so we see here a sketch of their experimental apparatus. So it's basically a standing wave resonator, which is driven by 2 loudspeakers here. So they proceed to LDV measurements, but the important point is that they have made measurements for different thermal conditions applied to the wall of the waveguide. So we have an uncontrolled thermal condition, we have an insulated thermal condition, and we have an isothermal thermal conditions for which the waveguide is placed into a water tank. What they have shown is that, so these figures represent the spatial distribution along that direction of the axial component of acoustic streaming, and this is the transverse distribution of the axial component of acoustic streaming. So they have shown that if we increase the acoustic level, we have a strong difference between experiments and theory, and they have also shown that the thermal condition applied to the wall impacts the spatial distribution of acoustic streaming, as we can see in these 3 different curves. So finally, the temperature distribution as well as inertia effect impact the distribution of acoustic streaming. These are other experimental works that we have made in my lab a few years ago. So this is still the measurement of acoustic streaming using LDV, but in a specific device which is called a closed-loop traveling wave resonator. So this simply consists of a closed-loop waveguide which is connected to two loudspeakers. In such a device, if both loudspeakers are driven in phase, we will generate an acoustic standing wave as it is represented here. So this is the acoustic velocity, this is the acoustic streaming velocity. So from this work, we have retrieved some theoretical results devoted to the calculation of acoustic streaming, and in particular, we have shown that if we have a traveling wave, so if we have a pi/2 phasing between both loudspeakers, then we will generate a traveling acoustic waves, and the resulting acoustic streaming will be non-zero across the section of the waveguide, and this is what we see here. But actually, the main reason why I wanted to show you these results is what we observe here for the distribution of acoustic streaming. So we can see that it's very complicated, and this is due to the fact that we have a geometrical singularity close to the loudspeaker. So the geometrical singularity itself is a source of acoustic streaming generation. And the last experimental work I wanted to show is the only one I know for which we placed a stack within a resonator and we look at acoustic streaming. So these results have been obtained by Solène Moreau using LDV. And what they have shown, so this is the resonator, this is a stack, and they have shown that if the stack is placed close to a velocity antinode, then the spatial distribution of acoustic streaming outside the stack will be similar to the one obtained in an empty resonator. But if the stack is placed close to a velocity node or at higher amplitudes, they have shown that it seems that we have additional streaming cells next to the stack. And obviously, this will impact heat transport by acoustic streaming in a thermoacoustic engine. So from the engineering standpoint, we do not know much about prediction of acoustic streaming, but we know that it impacts the thermoacoustic amplification. So we need to find some solution. So what we can do is, for instance, to suppress the so-called Gedeon streaming that goes like this in the loop. We can use, for instance, a membrane which is transparent to acoustics but not to the mean flow. Or we can use what we call a jet pump, which is an asymmetric constriction that when it is placed in an oscillating flow, it will generate a pressure drop, an asymmetric pressure drop that will generate a steady flow which is used to counteract the steady flow due to acoustic streaming. So to prevent from loss, we add some loss. But it works. Now concerning the relay streaming in what we call the thermal buffer tube, an empirical solution that has been found is to slightly taper this thermal buffer tube with a small angle, 1 degree here. And also it works. We do not know exactly why, but it works. Right. So let's go to the fourth nonlinear process, which play a role in the saturation of the thermoacoustic instability, so which is aerodynamical and thermal edge effects. So we know that when a flow passes through a geometrical singularity, there will be vortex generation with subsequent losses. So in thermoacoustic engines, we have many geometrical singularities, and we need to evaluate the subsequent losses. What we can do is to use established results for steady flow and adapt them to oscillating flow. But things are not so simple. We have to wonder if this quasi-steady assumption is valid or not. And also, another point is that at the stack termination here, we may have also some more complicated processes like vortex shading or high nonlinearity in temperature fluctuations that can impact heat transfer between the stack and the heat exchangers. So let's make a focus on these effects. So There has been many studies, computational and experimental studies of effects at the termination of a stack. And what we can say to summarize is that at low amplitudes, the losses due to vorticity are the same order of magnitude than what we could estimate from a steady flow approximation and a time averaging. But at large amplitudes, we may observe some more complicated process like vortex shading. So these are PIV measurements of the vorticity field, and we can see here clearly some vortex shading. And the presence of this vortex shading may be responsible for an oscillatory heat transfer between the heat exchanger and the stack. So it's not very clear, but we assume that this might play a role, an important role in the heat exchange between the stack and the heat exchangers. But we may also have some singularity in terms of heat transfer. And this may impact also the operation of a thermoacoustic engine. The reason is that when a gas parcel goes through the stack termination, it will abruptly pass from a region in which the processes are polytropic to a region where the processes are adiabatic. And this abrupt change in terms of heat transfer will generate high nonlinearity in the temperature fluctuation, even if the pressure fluctuations are harmonic. And this has been shown by Vitaly Gusev in the case of a simplified modeling for an inviscid fluid. And this has also been confirmed from DNS by David Marks. So in this picture, we see the temperature oscillations in function of time at this point, which is close to the stack end, and for different values of the acoustic Mach number. So this is for a low Mach number, and this is for a high Mach number, and we can clearly see that there is a strong nonlinearity in the temperature fluctuations. So how this high nonlinearity will impact the advective in transport between the stack and the heat exchangers, that's not clear. Okay, so finally, from this effect, there exist some open questions regarding the heat transfer between the stack and the heat exchanger. So those effects due to vortex shading and high nonlinearity in the temperature fluctuations. And if we just want to estimate some losses due to vortex generation, what we can do finally is to get an order of magnitude estimate is to use established results for steady flow. So for instance, is this famous book by Hidolczyk. We can find the expression of pressure drops for a flow like this way and a flow this way. And finally, we make a time averaging to adapt this to an acoustic motion, and we find finally that the losses are proportional to the velocity, the power of 3. Okay. There's a last effect that I should discuss, but I will be very brief with this effect because things are not clear concerning the transition to turbulence. Okay, so the transition to turbulence in straight ducts for steady flow has been very extensively studied, but it has been very poorly studied in case of oscillating flows. So these graphs come from hot wire measurements that was made by Omi, and they show that at low amplitudes we have, say, a laminar description of the flow, but if we increase the amplitude, we can observe some erratic motion of the fluid during the deceleration phase. So we may have some losses due to this. But the specificity of this oscillating flow compared to steady flow is that in that case we need two dimensionless numbers to describe this transition to turbulence. That are, for instance, a frequency parameter, so the Strahl number, for instance, and an amplitude parameter, which is the acoustic Reynolds number. And some authors have made some measurements using LDV, hot wire, or visualization of this transition to turbulence. So here I show a stability diagram of, obtained by different authors. So these lines corresponds to the transition to a conditionally turbulent regime. So this is laminar, this is conditionally turbulent. What we can see here is that these results, which has been obtained by Merkley and Thomad, and which has been confirmed by a French team recently, so we see that the transition line is different from the one obtained by many other authors. Now, if we want to understand more deeply why, we...
Can you explain a bit more what I'm looking at?
Okay, so this is, I'm sorry, this is the Strual number. This is the acoustic Reynolds number. And these lines corresponds to the transition between a laminar regime and this is a conditionally turbulent regime. Okay, and so these are the experimental conditions that was used by the different authors, and what we can see is that finally the only authors that have used some frequency which are in the audible frequency range are Merkley and Thomad and also Moreau et al. And they obtain a transition which is different from the one obtained by the other authors. So this means that there's a limit, maybe around a Strual number of order unity, for which the quasi-steady assumption is not valid. Now, if we want to estimate some losses, it is all the more difficult. So I will not try to do it, but I need to say that in the design software Delta EC, they propose once again to use established result for steady flow, so typically the Moody's chart, and to adapt these results for oscillating flow. So this approach is questionable, and actually we do not know accurately the losses due to turbulence. What we can do from the engineering standpoint is to polish the internal surface of the duct, or to use what we call flow straighteners at some T-junction, for instance. Okay, so now I will pass to another topic, which is the dynamics of thermoacoustic oscillators. So why? Let's assume that we have a thermoacoustic engine, like this, for instance, and we make experiments, which are these data points, and this is the results of a modeling. So if we want to fit the model with theory, what we can do? We can adjust some parameters that we do not know, but we do not know how to do it because we cannot dissociate the role of each of the nonlinear processes that I discussed. So a possibility to try to get a deeper physical insight is to study the transient regime. Because there are much more information in the transient regime than in the steady state operation. We can observe some highly complicated dynamics of the thermoacoustic instability. So for instance, we can find hysteretic loops in the onset and damping of the engines. We can see some spontaneous onset and damping of the waves that I will discuss in a few slides. And we can also observe some complicated dynamics that has been beautifully called here the fishbone-like instability. A key point is that each of the processes that I have discussed operates with its own time scale. And so due to this, we can get information of these processes in the transient regime. So let's go back to BASIC and let's ask if we are able to reproduce the dynamics of the wave amplitude growth in simple device like the closed loop stack-based traveling wave engine or even the thermoacoustic laser. So let's begin with the closed loop thermoacoustic engine. So here is a sketch of our experimental apparatus. So we have a stack and we have a hot heat exchanger and we measure the temperature at this side of the stack. So the experimental protocol is as follows. We just apply a heat input just below the threshold of the thermoacoustic instability And at some time, we put a power increment in order to generate self-sustained oscillation. What we can see is that at low increment of heat power, we can observe this spontaneous onset and damping of the acoustic wave. And this onset and damping is accompanied with significant variations of the temperature at the outside of the stack here. For larger values of the heat input, we can reach stabilization of the acoustic wave. But an interesting point is that the temperature that is reached in steady state is much lower than the temperature we have just before the onset of the thermoacoustic instability. So this means that the shape of the temperature field strongly impacts the thermoacoustic amplification. And it seems also that nonlinear effects which involves heat transport by sound seem to play a major role in the saturation of the wave. So let's try to describe this theoretically. And let's begin with the description of the thermoacoustic wave amplification. So to that purpose, we consider what we call here the thermoacoustic core, and we consider that we know the temperature distribution along this thermoacoustic core. So we can easily calculate the transfer matrices of this thermoacoustic core as well as the lossy propagation in the remaining of the waveguide. And by connecting this, we can obtain a characteristic equation. And we can solve this characteristic equation by introducing a complex angular frequency. The real part of this angular frequency will correspond to the working frequency of the engine, and the imaginary part here will correspond to the thermoacoustic amplification rate. So if it's positive, we have wave amplification. So it's a weakly nonlinear approach that we use. Now, we need to describe unsteady heat transfer. So what we do is that we use a one-dimensional description of heat transfer within the thermoacoustic core. So we account for the heating, we account for heat exchange with the surrounding walls, and we also account for nonlinear processes, which are the heat transport by sound here, and also the forced convection due to the Gedeon streaming, which goes like this. So I won't go into details. These are simply the equations that we need to solve. So this is the acoustic streaming. This is the effect of acoustic streaming in the stack. And this is the effect of acoustic streaming in this part, which is called the thermal buffer tube. And the effect of thermoacoustic heat flux is taken into account in the form of an acoustically enhanced thermal heat diffusivity. So to compute the transient regime, we have to solve this set of equations describing unsteady heat transfer with this equation that describe thermoacoustic wave amplification. Just a word about this equation, which describes the fact that the time delay for streaming establishment should be taken into account. It takes typically about 10 seconds for the streaming to be established after we have the increment of acoustic power. We can also account in a simplified way of minor losses in the same way as I discussed previously. Okay, so these are the results. On the left side, these are experiments. On the right side, these are simulations. So what we can see is that from the simulation, we can reproduce only qualitatively this switch on-off process of the thermoacoustic instability. And from the simulation, what we can say is that this switch on-off process is due to acoustic streaming. So let me explain this. So in this figure, you see the transient regime of wave amplitude growth here, and this is the spatial distribution of the temperature field at different moments along the transient regime. So this is at the beginning. And so at this time, we can see that the temperature difference between both sides of the stack has already significantly decreased. But we can also see, so this point is lower than this point. But we can also see the effect of the convection that acoustic streaming, which change the shape of the temperature field. And the shape of the temperature field in this part, in the thermal buffer tube, will act as a mixer of counter-propagating waves, and this will change the pressure, the velocity, and the phase shift between pressure and velocity within the stack. And this may provide additional amplification because we see that the wave is still increasing here. So finally, the effect of acoustic streaming is not only a reduction of the temperature gradient, it's less trivial. And we can also say from our simulation that under some circumstances, the model says that if we account for acoustic streaming, we will reach a steady state amplitude which is higher than without acoustic streaming. Okay, I need to go faster, so I will go faster only for this part. So now if we do the same for a standing wave prime mover. Let's make experiment once again. So we use the same experimental protocol, and surprisingly, we obtain the same kind of results. I mean, if the stack is placed close to the rigid plug, we will simply have a steady state operation with a stable finite amplitude with an overshoot here. But if the stack is placed in the middle of the duct, we still observe this spontaneous onset and damping of the wave. But we do not have Gedeon streaming. So the question is, do we have Rayleigh streaming? So we have tried to describe Rayleigh streaming in this kind of device, but I need to be very brief. So what we can do first is to calculate the spatial distribution of acoustic streaming. So these plots represent the spatial distribution of the streaming mass flow. So this is in one pore of the stack, this is in the waveguide. And we can see clearly that it is at least two-dimensional, and we have a one-dimensional description of the phenomena in our modeling. So we need to make rough simplification. And another point is that in these calculations, we treat a pore of the stack and a waveguide as isolated system. And so there's a problem at the connection between the waveguide and the stack for which we do not have the continuity of the mass flow. So we need to use a very, very simplified approach, but we have tried. So I will only summarize this. What we do is that we consider that the distribution of the streaming cells looks this way. So this is in the waveguide, this is in each pore of the stack. And we will, to account for this effect in unsteady heat transfer, we will consider that we have an inner zone with its own temperature and an outer zone with its own temperature, and we will make a spatial average after that. And we need also to account for the heat removed by acoustic streaming at the stack interface. So what we do is summarize in this picture. We consider that this configuration is equivalent to the configuration where we have a mean flow which crosses a grid at constant temperature, and we can estimate this heat flux. Okay, so these are the equations that we have to solve. Okay, I don't go into details, and these are the results we obtain. So these gray lines represent experiments. The blue lines represent the modeling for which we account for both acoustic streaming and heat transport by sound in the stack. This is for the only acoustic streaming, and this is for the only thermoacoustic heat pumping effect. So we cannot reproduce this spontaneous onset and damping of the wave. So the question is, what is the mechanism responsible for that complicated operation? And we could also wonder if we can claim understanding the operation of this very simple engine. How can we claim we understand it if we cannot reproduce this complicated dynamics? Okay, so I will now pass to the last part of my presentation, which is still devoted to the dynamics of thermoacoustic oscillators. But here I will look at the thermoacoustic oscillator as an interesting dynamical system, which is driven by heat and which exhibits complicated operations. So what we will do in what I will present in the next slide is the effect of nonlinear coupling between a thermoacoustic oscillator and an external sound source. So I will look at two things. The first one is to revisit some universal aspects of synchronization phenomena, mainly for teaching purpose, but it's interesting. And the second topic will be to investigate the active control of a thermoacoustic engine in order to increase its efficiency. So let's go to synchronization phenomena first. So synchronization refers to something that has been first evidenced by Christian Huygens when he was studying pendulum clocks. So if we have two autonomous oscillators, say two pendulum clocks, which are very similar but not exactly the same, so that they have their own different frequency. If we couple these two pendulum clocks with a beam, Huygens has observed that each pendulum will shift its own frequency in order that they have the same frequency, but we will also have a phase locking, so they will move this way or this way. So we have frequency locking and phase locking. So synchronization phenomena are widely used and known in many fields of physics, for instance in biology, in electronics, in physics, and even in social life. And it has also been studied in the field of acoustics, for instance by Lord Rayleigh, who have studied the synchronization of organ pipes. And he was the first to observe what we call the quenching phenomena, for which both organ pipes will almost be reduced to silence due to their nonlinear interaction. So this is called beating death or quenching. But even recently, a German team has made this kind of study of the synchronization of an organ pipe with an external sound source. So what we want to do here is to take a particular thermoacoustic oscillator, which is the thermoacoustic laser. So you can recognize here the thermoacoustic laser, and this is a loudspeaker enclosure. And we have some generic apparatus around. And so we will try to control this thermoacoustic oscillator with the loudspeaker enclosure. So what we do is that we fix a heat power above the threshold of thermoacoustic instability, and we fix both the position of the stack and the distance between the loudspeaker and the thermoacoustic oscillator. And then we proceed to measurements in which we vary the frequency of the loudspeaker enclosure and the amplitude of the voltage provided to the loudspeaker. In terms of signal processing, what we can do is an Hilbert transform of the data, from which we can calculate the amplitude modulation of the signal, as well as the instantaneous phase difference between pressure and electric voltage. And what we will observe is 4 different possible states. The first one is perfect synchronization, for which the oscillator will shift its own frequency to that of the loudspeaker. The second one is imperfect synchronization, I mean imperfect phase locking. So the frequency of the loudspeaker is different from that of the thermoacoustic oscillator, but the instantaneous phase difference stays bounded. We have also the quasi-periodic regime, for which this phase difference is not bounded, and we can also observe quenching. So in the next slide, these are the results. So this is the frequency of the loudspeaker. This is the voltage applied to the loudspeaker. And this is the so-called Arnold tongues. So we have a region of synchronization here, another region here, for which the thermoacoustic oscillator will shift its own frequency in order that it is twice the frequency of the loudspeaker. We have another Arnold tongue here, and this is a region for which we have quenching. So if we look into details, so let's look at these points. So these points corresponds to synchronization. We do not see any beating. At this point, we see beating, so we could think that there is no synchronization. But actually, if we look at the instantaneous phase difference, we see that the phase stays bonded, which means that the loudspeaker imposes its phase to the thermoacoustic oscillator. So we have some kind of a synchronization process. And this case corresponds to quasi-periodicity. Here, this is a region for quenching. So if we are within this region, we have this spectrum. And if we are outside this region, we have this spectrum, which is typical of a quasi-periodic regime for which we have the frequency of the oscillator, the frequency of the loudspeaker, and many combination frequencies. So the interesting point with that results is that we can observe some phenomena which are universal for synchronization phenomena. But we can also observe some phenomena which are intrinsic to the thermoacoustic oscillator itself. So we may have information from the thermoacoustic itself only from these measurements. So for instance, we can see here that this Arnold tongue is highly asymmetric. And actually, we do not know why the quenching zone is around half the frequency of the thermoacoustic oscillator. It's not clear. Okay, now what occurs if we operate the engine in such a way that it is in an integrate and fire regime? So we adjust the heat power input in such a way that we have a spontaneous onset and damping of the wave. Now what occurs if we switch on the loudspeaker at a frequency which is close to that of the thermoacoustic oscillator? So in these results, we switch on the loudspeaker at this time and we switch it off at that time. And here we increase the amplitude of the loudspeaker voltage. So what we can see is at low amplitudes, there's nothing except that the wave does not switch off completely, and we have here a small quasi-periodic regime. For larger amplitude, we can observe synchronization. So the thermoacoustic oscillator will shift its frequency to that of the loudspeaker. But the interesting point is that by acting with loudspeaker, we can stabilize the amplitude of the thermoacoustic oscillator itself. So the question is it simply quenching, or is it a more complicated nonlinear interaction between the thermoacoustic oscillator and the external sound source? It's not clear for the moment. And now let's conclude. So I have looked through synchronization phenomena, but there's another interest in trying to force the thermoacoustic oscillator with an external sound source in terms of energetic application for a thermoacoustic engine. So the basic ideas are that above the threshold of thermoacoustic engine, the oscillator is out of control. So the basic idea is to try to use an additional source that will try to control at least partially the thermoacoustic oscillator in order not to decrease the wave, but to increase the wave, because we want to have a high acoustic power in our device. So we have already made a proof of concept study in that kind of device, so a closed loop waveguide, and these are two sources, two loudspeakers, that are driven in both amplitude, and we control also the phase shift between the signals provided to these two loudspeakers. And we have demonstrated in that device that under some circumstances, we can have an additional acoustic power into the closed loop, which is larger than the power that we have provided to the loudspeaker. So this proves that we have a nonlinear interaction that increases the efficiency of our engine. So now what we will try is to make this same kind of study, but in a different engine, which is this one. So this is a thermoacoustic Stirling engine, which uses a regenerator here, and which is connected to a load which is a loudspeaker which is used as an alternator. So from it we provide electricity. And here you can see that we have an additional acoustic source which is related to a microphone via a phase shifter, and we control the phase. But I won't go into details because Comme-Olivier will make a presentation about these works in the next workshop. So now let's conclude. So my conclusion will be very brief. In the first part, I have shown that the design simulation tools have some limitations which are related to the one-dimensional description of the phenomena, to a linearization of the governing equation, and to the fact that they only predict steady state. In the second part, I have shown that the processes that control the saturation are well identified, but however, it's difficult to account for these effects in an actual engine which has a complicated geometry. And finally, in the last part, I have shown that even simple thermoacoustic devices are not so well understood, and we may start with this simple device before trying to describe more complicated devices. Okay, so that's the end of my talk. So just a few words about my city. So this is Le Mans City. We have a beautiful cathedral, and maybe you know the famous car race. And we also have an acoustic lab in Le Mans, so if you want to visit the lab, you are welcome. And we have here the thermoacoustics team, so myself, Pierre Cloton, Gaël Poignant, and Comme. So thank you for your attention.